we saw this, the way we define dual, this is sort of obvious. And if you remember, we picked some multiplier for each constraint. Those were the yi's. And then we said, if I ensure that every column adds up to at least this much, then this is the weak duality theorem. It says that if x and y are feasible solution, some feasible solution, then C transpose X is less than or equal to B transpose Y. And as a corollary, max of primal is less than or equal to min of dual. Okay, we'll prove why this is true, but the way we said, okay, I want to get, remember the way I motivated dual is I want to get some upper bound for this. I looked at various combinations of these constraints, and I said, why just look at constraints, you can add, multiply, and various things. Ensure that each column is at least the corresponding coefficient of C, which corresponds to this constraint. Then, the objective function is upper bounded by that objective function. Okay, so why is this true? The proof of this is pretty easy. C transpose is less than or equal to, from here. C is a column matrix. So C transpose is less than or equal to, because Y is a feasible solution for the dual, transpose of this, which is Y transpose A, which implies C transpose X is less than or equal to Y transpose A into X. This is same as Y transpose into A into X. And X is a feasible solution for this, so that's less than or equal to. So what I have shown is, no, I've taken the transpose of this, which is basically Y transpose A. And Y transpose B and B transpose Y are same, because this is just a number. It's an inner product, it's just one number. Okay? This is same as B transpose Y, and that's what I wanted to show. So in particular, if X and Y are, if you take the max of this as your X and min of that as your Y, then you have max of the primal is upper bound and min of the dual. Some other corollaries is, okay, so sometimes this LP may be infeasible. What does it mean by infeasible? There is no point that satisfies this constraint. Right? So if you write down your polytope, it's empty. So it's just going in various directions, that the common intersection is empty. So sometimes it may be infeasible. Sometimes it may be unbounded, meaning your objective function value, the X that maximizes could be infinity. Okay? Now here are some interesting if primal is unbounded, then dual is infeasible. And similarly, if dual is then primal is infeasible. Why? Because if the dual is feasible, then any feasible solution, the objective value is an upper bound for the primal. So primal cannot be unbounded. Right? Because of this, if the primal is unbounded, then dual has to be infeasible, because if the dual is feasible, any feasible value, the objective function is an upper bound on the primal. And similarly, if the dual is unbounded, primal has to be infeasible, because any primal feasible solution is a lower bound for the dual. Dual is a minimization problem. Unbounded dual means that the objective value is minus infinity. Okay, so these are some interesting properties of the dual, and it also turns out, which this is something we will not prove, it requires some geometric view of the whole thing, is that the strong duality theorem if X is primal optimal and Y is dual optimal and both are bounded, then C transpose X is actually equal to B transpose Y. Okay, and let's see, when do you have, so this is, I'm saying these two are equal, which means that this quantity is equal and this quantity is equal at the optimal, right? If you look at this inequality I have written down, if they become equal, I mean, these are the points that contribute to inequality, they also have to be equal, right? So the corollary is at optimality, both primal and, this is an important property which we will use for sometimes algorithms. At optimality, C transpose minus Y transpose A into X is 0. Okay, so this is also an inner product. C transpose is a column, row vector, minus Y transpose A. Y is, what kind of dimension is Y? It's M dimension. Okay, so this is Y transpose is 1 by M. Yeah, 1 by M. So 1 by N. This is in 1 by N, this is in, so it's, you subtract this out and multiply by X, which is an N dimensional vector. So this is all N dimensional vectors, and you get this term 0. And similarly, this is also. Yeah, Y transpose into AX minus B equal to 0. Okay. Because of this, at duality, you have these two constraints are same, and these two values are same, which means is these intermediate things are actually equality. That's all I'm saying. Okay. So let's see, what is this saying? X, Y are all greater than or equal to 0. So, let's look at this. Ax is always less than or equal to B. So, Ax minus B is a negative number, or less than or equal to 0. And so, you have summation yi into AXI minus BI or whatever is equal to 0. Now these constraints may be satisfied with equality, or so this may be 0 or less than or equal to 0. Right, and something similar there. So what happens if this constraint is not an equality? What does that mean? What can you deduce? Okay, so remember this is a bunch of constraints, right? You have various constraints here, and at optimality, some of these constraints may be satisfied with equality, some would be less than or equal to. Suppose you have a constraint which is not satisfied with equality, which means that that corresponding term would be negative here. And how can the sum be equal to 0 if you have a term which is negative, because there is nobody positive to kill it. Corresponding yi is 0, exactly. So the if i.e. if a primal constraint is not tight, corresponding dual variable is 0. This is at optimality. We are talking about at optimality. And similarly, if you just expand out this whole thing, again, C minus A transpose Y is less than or equal to 0 because of this constraint if Y is feasible solution for the dual. So if a dual constraint is not tight, corresponding primal variable is 0. Okay, so this is called complementary slackness condition. I mean, there are algorithms, we will actually look at maybe an example next time, where you somehow find the optimum solution without necessarily solving the LP. Okay. Yes, LP is solvable in polynomial time, but it's still a complicated algorithm. And if you want to solve this LP without really solving the LP, we use what is this called primal dual method, where we keep this condition in mind that when at the optimum, in fact, this is also useful for approximation algorithms. We will see examples. That this complementary slackness is very useful. That I start with some variable and then say I want to move to something better. I'm going to be guided by this complementary slackness condition because that's what happens at the optimality. Okay, good. So we'll come back to complementary slackness condition and its uses later. But all you have to remember is this: that if you have so this is complementary slack. So if you have a slack in one variable, the corresponding one constraint, the corresponding variable is 0. Okay. So if you expand this, it's the same thing. If you have a slack here, the corresponding primal variable must be 0. Okay, so towards the end, last time we saw the dual of matching, and it turns out to be vertex cover, right? Modulo 1 point that matching is not an LP because our variables which correspond to edges being in the matching or not, they are all 0 or 1. So it's an integer linear program. Nevertheless, if you just relax the constraint and think of it as an LP, then we get, similarly vertex cover is also not an LP because we are setting the variable 0 or 1, and so if you think of it as an LP, then one is a dual of the other. Okay. And okay, so we'll see another example. I was going to do flow and then come back to deal with the fact that for certain kind of graphs, the LP solutions turn out to be actually integral solutions, which is very useful. Right? That means that those kind of integer linear programs are solvable in polynomial time. Because you just relax the LP and solve it, you automatically get integral constraint. So that's the second part we'll do. Let's look at max flow and formulate it as a prime, look at the primal and the dual and how they look like. Okay, so what is max flow? Right? So what do you want to maximize? Summation x SV. SV is an edge. So what are the, so you have a vertex set, you have an edge set, and then there is this capacities on the edges, and then there is this two vertices S and T, right? So our variables are, what is the flow value on an edge? That's a variable. X ij represents the flow value on the edge ij. You want to maximize these edges flow out of S. And what are the constraints? For all V in V minus ST, summation UV in E x UV minus summation VU in H is equal to 0. So one thing I did not say, if greater than, if less than or equal to constraint, the corresponding variable is greater than or equal to 0. If greater than or equal to constraint and this, the corresponding variable is greater than or equal to 0. But if you have an equality constraint, then the corresponding variable is unrestricted. Okay, you can go back to the way we define motivated duality, and you will see that it's there's no constraint on that corresponding variable. Okay, so let me just make a note here. Yeah. Fine. So what are the other constraints? Capacity constraint, right? So for every UV in E, X UV is less than or equal to its capacity. And all the X UVs are greater than or equal to 0. Okay, let's write the dual. Okay, so how do you write the dual? So it's a minimization problem. So you have a variable for every constraint. So these constraints are for every vertex except S and T. So let's define some variable YV for all V in V. Okay. Maybe I'll use YS, YT also, I'll come back to it, but for now, it's V minus ST. I'll have a variable. And for every edge, I have this capacity constraint. So let's have a so these are my dual variables. Dual variables correspond to primal constraints. Okay. Fine. So what is the objective function? So the objective functions, you get your coefficients from the right hand side, right? So the right hand side are 0 and CUV, right? So it's min summation CUV into ZU for all UV. Okay, it's a minimization, and the right hand side CUV for every ZUV and 0 for every YV. So that's my objective function. And my dual constraints correspond to primal variables. And primal variables for every edge. Every edge there is a variable XUV. So the dual constraint should correspond to every edge. So for all UV in edge, right? Suppose U is not equal to S and V is not equal to T. We'll handle that first and then we'll look at edges out of S, edges into T, because the constraints are slightly different. So for every edge, what are the, so you're going to pick the column, right? Every column, the coefficient are 1, so that's going to be the right hand side will be, no, not everything is 1. Right? For any, 1 or 0. For any edge out of S, the coefficient is 1, for other edges, coefficient is 0. So that will be the right hand side. Okay. So for any edge where S is, it's not an S thing, the right hand side is 0. So you will have a greater than or equal to 0 here. So what do you get? You pick an edge UV. Okay, so S is here, T is here. This edge, what are its column? What are the so here it's 0. What are the coefficients here? Right? So there will be 1 ZUV because it's appearing exactly 1. So ZUV will be there with a 1. And then YU minus YV, right? Because whenever you have this UV edge is there, you will have the corresponding YU, right? This corresponds. So if you view it from U, you will have a constraint of all edges going out of U. So with the positive coefficient, if you view it as a V, there will be a minus corresponding to that edge. So it's plus YU minus YV is greater than or equal to 0. Now let's look at edges out of S for this kind of edge. Again, you will have a ZSU, right? ZSU because of that capacity constraint. And there won't be anything coming from S. So the positive thing won't be there. But at the U end, you will have a minus term. So minus YU is greater than or equal to 1 here because of this coefficient. Right? And for all T, UT or VT in E, again you will have Z, VT. The plus thing will be there, but not the minus. And greater than or equal to 0. And your ZUVs are greater than or equal to 0 because of this constraint, but the YUs are unrestricted because of the equality constraint. Okay, so I want to make these constraints sort of uniform for all of them. So I will introduce some YS and YT say that they all look the same. Okay, so what can I do for ys? So I want to write this as follow the same pattern plus ys greater than or equal to 0. So let me put ys equal to minus 1. If I write ys equal to minus 1, then this is the same as what I had before. And what should I put for yt? I want to put yv minus yt is greater than or equal to 0. So yt is 0. So that means all my constraints are for every edge uv, zuv plus yu minus yv is greater than or equal to 0. Yeah. So it's uniformly with this simpler thing about s equal to minus t and t equal to 0. Okay, now we're going to show two things. Okay, first claim is this is nothing but this dual of max flow is the LP relaxation of min ST cut. And why do I say LP relaxation? Because it's again, as a cut, these guys have value 0 or 1, but we'll deal with that later. So ignore the fact that I might want the variables to take integral values, in particular ZUV and the YUs. But if you just ignore the fact, similarly the XUs I may want integral if all the capacities are integers. Let's assume the capacities are integers. Then I claim that this is nothing but a min cut LP, min ST cut LP. So I'll prove by showing that this opt value is actually equal to the value of the min ST cut. Okay, I'll show by showing greater than or equal to, less than or equal to. So if you have a min ST cut, okay, then define y equal to minus 1 for all u in A and 0 for all u in B, and z uv to be 1 for all uv in the cut, 0 for other edges. Okay, I claim that it satisfies these constraints. So take any cut, not necessarily min ST cut, take any ST cut, and I suppose I throw in the values that for everything here. So all these guys get minus 1, and all these guys get 0, and any edge in the cut I'm going to put 1, and any edge inside is 0. Then I want to argue that this is my constraint, right? I already told you that this is the constraint for every edge. Is it clear that it satisfies this? So if you have an edge inside A or inside B, ZUV is 0, and both of these guys get the same value, so they cancel out. It will be equal to 0. And if you have an edge across, ZUV would be 1, and this difference would be minus 1, because one of them would be, this would be minus 1 and this would be 0, so 1 minus 1 it will be 0. So all these constraints are satisfied. So opt of the dual LP is less than or equal to min cut. Right? Because min ST cut is a feasible solution here. If you give me min ST cut, I can convert it into a feasible solution, satisfies all the constraints. So it's one solution. So the opt of the LP, if any, may be less than or equal to the min ST cut. Okay, and I will show you the converse as well. That from the opt solution, I will obtain a cut whose value is equal to or less than or equal to the opt of this. Right?
So we told YV, these are unrestricted.
Yeah.
And we are defining it while is equal to -1, so we are restricting it.
No. What did I do? You give me a ST cut. I will give you a feasible solution for the LP from the ST cut. So all I'm saying is any cut satisfies this LP. That's all I'm saying. The translation from the cut to the value of these variables is what I have done. And give me an ST cut, I'll translate it, I'll set the variables. This is my choice. I'm going to do it. And then I'll say, okay, now plug it in. You will see that this opt value, I didn't say this. This opt value is exactly the capacity of the cut. Right? Summation CUV, ZUV. Whenever ZUV is 1, it's in the cut. So this objective function. So the opt of this LP is, if any, less than or equal to the min cut value, because min cut in particular satisfies this LP. Now I'll show the converse. Let Z star Y star be an opt solution for the LP. Then I'll produce you a cut whose capacity is less than or equal to that objective function. So that will show that min cut value is equal to this. This is exactly min ST cut LP. So this is an interesting way of proving this. I don't know any other simple way. We're going to use some randomization to prove this. So what we'll do is following. I want -1 and 0, right? Okay, so pick some R in -1, you might even take -1, comma 0. So this is uniformly at random. Some number in the interval -1, 0. And I'm going to define my S as all V such that its YV is less than or equal to R and A, and B is the rest. And I'm going to argue that this is actually a cut, an ST cut. The fact that it's an ST cut is clear, right? So in particular, S would be here. So you pick a random value in this closed interval, half closed, -1, 0, And then anything which is less than or equal to that value, I'm going to put it in A and the remaining in B. So in particular, since ys, so solve this LP and you get your yz values, but this LP sets ys to be -1, yt equal to 0, and other y's and z's it can set whatever way you want to minimize this objective function. So ys, s would be definitely in A and t would be in B, so it's an ST cut. Let's understand the expected size capacity of the cut. If I pick an edge UV, what is the probability that it is in the cut? Because remember, this is a randomized algorithm, doing a random process. Probability that an edge UV is in cut is equal to probability that, so it's a directed edge, that U is less than or equal to R times probability that V is greater than R. Right? That's how it can be in the cut. It's a directed edge UV. So what is the probability? This is where it will be in the cut. Which means that my R is in the interval UV. This is same as saying probability that R is in this closed interval U comma V. Okay, what is this probability? That I'm picking a random value in the range -1 to 0. What is the probability that it is actually sitting in this range? So the length of this interval is 1, right? Yeah, 1, -1 to 0. So it is proportional to the length of this interval. Sorry, yu. Okay, yu is greater than or equal to yv is greater than or equal. So this is yu, yv. Right? That's the definition. So this is equal to yv minus yu. And it's quite interesting. I don't know any other. But since yv, yu are all feasible solution, or yv star, I'm using star, so let me use star. This is the optimum solution, right? But yv, yu are in this feasible solution, so yv minus yu is less than or equal to zuv, right? Right. So this is less than or equal to zuv star. Okay. So the probability, so you're doing a random process. So you solve the LP, and I'm going to give you a cut whose value is less than or equal to the value of the objective function. That's what I want to show. So I don't know, see an easy way of producing this cut. Let me do a random process. So pick a random value and split it like this. Then I show that probability that an edge is in the cut is at most zuv star. So expected size of, or expected capacity of the cut is, do this for every edge. So it's less than or equal to summation cuv into zuv star. Because for every UV, it's a linearity of expectation. For every UV, it is in the cut with this probability and you multiply it by this capacity. But this is exactly the objective function of the LP. So expected capacity of this cut is less than or equal to the optimum LP. So what is this expectation over? When I say expectation, what is this expectation over? What is my random choice? Where is the random choice in my this? So this expectation is over R. So I'm averaging. So I just pick an R and look at this cut value. Try a different R, look at the cut value, and I'm saying that this average is at most this much. So there must be an R for which this is at most this much, right? This is the cornerstone of probabilistic method, okay? There are a lot of very nice algorithms using this simple idea that if my average over a distribution is something, then there must be somebody whose value is at most that much. So there must be some R for which the cut value is at most this much. That's what I want to show. I wanted to show you is that there exists a cut. There exists an ST cut. So pick some, there is some R, right? From here, it implies that there exists an R for which there is no expectation. If you say there exists an R, the randomness goes away. There exists an R such that this cut value capacity would be at most that. So I've done both ways, that the optimum value, that if you give me a cut, I have produced a feasible solution to this LP, and if you solve the LP and give me the optimum solution, I have produced the cut whose objective function is less than or equal to. So this is exactly the min cut value, min cut LP. Okay, this is just actually cutting the LP. It just says partition your vertex set into two parts such that this corresponds to the capacity of the cut, and you ensure that whenever you have an edge that crosses the cut, these two guys are in two endpoints and two different partitions. So the only thing is that for my ST cut, I really want integral constraint. You know, ZUV might actually take some fraction values. So how do I deal with it? So now what I'm going to show now is that for these two problems we saw, one is this maximum matching and its dual is minimum vertex cover, max flow whose dual is a min cut. When you think of them as LP without worrying about integrality constraint, I will argue that the vertices of these LP are actually integral values. That means that if you want to solve the integer version of it, you just solve the LP and that's good enough, right? So, and why is that true? We will argue that this constraint matrix are special, that the vertices, the points on the vertices are actually integral values. Okay. So this is true for both bipartite matching. So there we needed bipartite, and here is just any directed graph. Okay. So and as a consequence, you have this max flow min cut theorem. Because of this duality, strong duality theorem, you know that at the optimality, max value of the primal and max min value of the dual are the same. So the max flow gives you max flow and min cut values are the same. And similarly, in bipartite graphs, maximum matching is equal to minimum vertex cover. Okay, so let's just go back to this matrix, LP. So I have max, and the constraints are AX less than or equal to B, X greater than or equal to 0. Right? So what is the vertex in this simplex method or in this LP? So there are M constraints, right? A is M constraints, and N variables. M is much larger than N. So if you pick some N constraints, some of N of these constraints and solve the equality, then what you get, the solution to that N by N matrix is a vertex. Okay, so because in 2 dimension, what is a vertex? It is just the intersection of two lines. Okay, so that means you take these two lines, they are actually half planes if you write them as inequalities, but if you write them as equality, these are two lines and that intersection is a vertex. Similarly, in a higher dimension, what you do is if you have M constraints and N variables, take N constraints and solve them with the equality, and the point you get is a vertex. So that's what simplex does. So how many such vertices are there? M choose n, because you choose n out of these m constraints, and m choose n. That's why simplex in the worst case is exponential. M choose n is like m power n, and simplex is not polynomial because it runs through every vertex. Okay. So now if I pick some n constraints, then what do I get? Let's look at this matrix A prime, which is, right, this is basically, you have this big m by n matrix, and out of which I pick some n, so I get an n by n matrix. And I solve x is equal to b prime. B prime would be the corresponding right hand side. Then x would be A inverse b prime, and I want this x to be integral. Okay. If you know Cramer's rule to solve this system of equations, so I don't know how many people remember this. So if I have an n by n matrix, right? And I want to solve x1, x2 up to xn is equal to b1 up to bn. I want to get xi. One way to do it is you remove the ith column, replace it by bi, look at the determinant of the matrix divided by determinant of the original matrix. So xi is determinant of ai by determinant of A, where AI is replace ith column by, right hand side, the B vector. This is Cramer's rule, where you can actually get the xi values for each I. So replace the first column by the B vector, do the determinant by determinant for getting x1, x2, x3, and you can get this for every xi. Now I want these xi's to be integers. Okay. When do I get these as integers? If the determinant of that matrix is plus 1 or minus 1, then there is, that's one sufficient condition. If the determinant of the entire matrix is plus 1 or minus 1, then there is no fraction at all. For every xi, it will be determinant of some number, which is if all the ai's are integers, then this would be some integer. There is no division happening, so it will be an integer. Every point would be integer. Okay. So this is one sufficient condition, and the only thing is I don't know A. There are different combinations for each vertex corresponds to a different subset of n rows, right? So let me insist my matrix to have this property that every subdeterminant, every subsquare determinant is 0 plus 1 or minus 1. Then such a matrix is called totally unimodal. Yeah. So totally unimodular is a matrix A is totally unimodular if every submatrix has determinant So now here is the following easy theorem. If your constraint matrix A is totally unimodal, then the vertices of the LP. And in particular, the optimum. Is integral. Oh, the total. This is clear, right? This is what we went through. All I'm saying is if the vertex of an LP is just the submatrix, the submatrix determinant is plus or minus 1 or 0. If it's 0, then you throw away that set of submatrix and move on to another submatrix. There's some degenerate vertex, that's what it is. And so what we will show is that, okay, so the proof of this is clear. That's how we sort of motivated this definition of totally unimodular matrices. Note also that every entry of the matrix is 0, plus 1 or minus 1, because that itself is a submatrix, right? And its determinant is its value, so it has to be 0, plus 1 or minus 1. Okay, the next theorem is, the vertices of the LP and its dual also. Why? What is the constraint matrix of the dual? A transpose. So every submatrix is also, has determinant 0 or plus 1, minus 1. The constraint matrix of bipartite matching and max flow.
So these should be integral.
Oh, yeah, all of these are integers. Yes. Or actually, yeah. Yeah. So A is anyway, we already ensure that 0 plus or minus 1. B values should all, B and B in particular, should be integers, right hand side. Yeah. Let's look at these two matrices, right? How are they, right? Or let's do something more general. More generally, if A is such that its entries are 0 plus or minus 1, sum of for any j, no, over I. If you add the entries on a column, right? J is some column, and you add the entries of this column, this is at most 2. there exists a partition R1, R2 of the rows such that for any column having two entries, two non-zero entries, one non-zero entry is in R1, other is in R2. Then A is totally unimodal. Okay. What do I want to prove? So, is the statement clear? Entries are 0 plus or minus 1. Each column has at most two non-zero entries, is what it says. Each column has at most two non-zero entries, and I have a partition of my rows, into R1, R2, such that if you pick any column with two non-zero entries, they are not both here, and it could be 1, 1, plus 1, minus 1, or minus 1, minus 1, all of this. Both cannot be here. So if you have a column, then 1, 1 would be here, 1, 1 would be here, or it's a plus 1, maybe minus 1. They are split like this. Such a matrix is totally unimodular, and then we will show that the constraint matrix of bipartite matching max flow have this property. Oh. Okay, at least for bipartite matching. Max flow, I think, is even simpler. Okay. So, what is a constraint matrix for matching? Matching, right? For every V, what do we say? Summation XE E is incident on V is less than or equal to 1. That's all the constraint is. Right? So there's, for every V, look at all edges going out of V, the sum of the XE value should be less than or equal to 1. So that's a constraint matrix. Okay. So how many rows are there? How many columns are there? And V rows, yeah. So I'll have a row for every vertex. And my column would be edges, right? So this is exactly the node edge incident matrix. Okay. And every column has at most two entries, right? I mean, this is clearly 0 or 1 entries are. Every column corresponds to an edge. So this edge, if it's a UV edge, then U will have a 1 here and V will have a 1 here. So exactly two entries will have 1. And if it is a bipartite graph, then this partition is basically this, look at the AB is my bipartition, then look at the rows corresponding to the vertices corresponding to A, corresponding to B, then any edge is between A and B. So the two ones corresponding to an edge are in two different parts. Agreed? So this bipartite, so this is true only for bipartite, because if it's non-bipartite, I might have two ones here and I can't really show that it's totally unimodal. In fact, I think we've seen example that for non-bipartite, it's not true that maximum matching, it's not integral. The optimum value is not integral. So here is what is the optimum maximum matching, right? The integral matching would be 1. You can't have more than one edge in the integral matching. But if I am allowing fractions, then I can put half here, and half here. So for every vertex, the matching size is at most 1. And the total objective function is the sum of the matching would be 1.5. So, and similarly, vertex cover in a non-bipartite graph, I can put a half here. Every edge is covered. The number of vertices I'll pick is like 1.5, whereas the non-fractional thing would be 2. You need 2 vertices. So this is not true for non-bipartite graphs, and part of the reason is because I can't split my rows like this, and here this property C tells me that I can actually split my row into. Okay, this is a sufficient condition. Now for max flow, I will give you a slightly different argument. Okay, what do I have to now show? That every submatrix has determinant 0, +1 or -1 for such a matrix. Okay, let's try and show that. Okay, good. So suppose, okay, so I'm working on this, or in particular, such a matrix. Let A prime be a minimal submatrix whose determinant is not +1 or -1 or 0. Okay, so that's my matrix. Now, so I want to arrive at a contradiction, right? Can you have a column in this submatrix with all zeros? Why not? Because the determinant would be 0. Can I have a column in this submatrix with exactly one non-zero entry? If I have a column with exactly one non-zero entry, let's say this entry, +1 or -1, everything else is 0, then
determinant of that will be some smaller submatrix.
Exactly. It contradicts its minimality, because what is the determinant of this matrix? If I expand by this column, it is whatever this entry into, remove that 2 entries and you have a submatrix. It's basically that submatrix. So this into that is not +1 or -1, 0, or means that submatrix is a even smaller submatrix which satisfies this condition. So what does this mean? Every column has exactly 2 non-zero entries, because it cannot be 0 non-zero entry, it cannot be 1 non-zero entry. So every column has 2 non-zero entries, right? There may be things like this. Okay. Okay, I'm actually talking only about bipartite matching. This looks too general. I don't know whether I have a proof of that yet. But let's talk about this bipartite matching thing. So every column has exactly 2 non-zero entries, and 1, 1 here and 1, 1 here. So look at the partition, right? So these rows correspond to, some of them correspond to my vertex set A and another correspond to my vertex set B. Now, let's say this corresponds to, look at what is A minus B. So if I take every column and because of the bipartite property, for every edge I have one endpoint here and one endpoint here. So the one is here and one is here. So if I multiply each row of B by minus 1 and add this entire, all the rows, multiply each of these rows by 1, multiply each of this by minus 1 and add, what do I get? Every column has two ones, exactly two ones. On one is in the top, on one is in the bottom. Right? So I am subtracting this minus this. So what do I get? I get all 0 weight, which shows that this determinant is actually 0. It's a linearly dependent set of rows. Okay, so this A minus B is a 0 weight, which means the determinant of this matrix is 0, which is a contradiction. Okay, is that clear? So it's just a node edge incident matrix on a bipartite graph is what the constraint matrix of the matching is. And you look at the submatrix where every column has exactly two ones. Since there is this partition of the rows, you take this rows, multiply by 1, take these rows, multiply by minus 1 and add them all. What you get is 0, 0, 0, 0, 0, 0, 0. So that means that this matrix has determinant 0. Okay. And for max flow, what is the constraint matrix? So constraint matrix is, so the rows correspond to vertices and edges, and the columns correspond to vertices.
You said B minus 2 number of rows.
Yeah. So for max flow, for now let's ignore this set of constraints, or maybe let's capture this. What is this set of, for every edge, it's basically an identity matrix. Okay, so I will have for every edge, no. Right, columns also correspond to
My variables are the ages, so column correspond to ages.
columns correspond to
The column is vertex and edge.
Achha,
columns correspond to edges, right?
correspond to all ages, and for ages we get one identity.
Yeah. So this correspond to edges, and these correspond to vertices, and so this is just an identity matrix. They really don't play much role here. And for every vertex, you look at an edge ij. So if this is I, there will be a +1 here, and whenever j, there will be a -1 here. That's all there is. And corresponding to that edge, there may be a 1 here. Okay, so let's ignore this. Okay, I didn't pay attention to this set of matrices, but I want to argue that this matrix is totally unimodular. Every submatrix has determinant. I mean, it should be easy here also. I think it's an identity matrix. But every submatrix, because the same kind of an argument here, the only difference is for every column you have a 1 plus 1 and 1 minus 1. Okay. So what you do is you look at a minimal submatrix whose determinant is not one of this. Then for the same argument, every column should have two non-zero entries. And the non-zero entries in this case are plus 1 and minus 1. So every column has a plus 1 and a minus 1. You add them all, they become 0. So at least this matrix has is totally unimodular. If I include this, what happens? Is that easy to see? Yeah, so if you have a bunch of rows, okay, if it does not include any of these rows, no problem. If it includes some of these rows, then maybe you multiply these rows by 2 so that you get minus 2 and these 2 will add up and cancel out or something. Okay, I don't. So this matrix is totally unimodular, it's clear because of this same kind of an argument. But why is every submatrix of this big matrix totally unimodular? If it includes some from here, some rows from here and some rows from here I managed to do, suppose. Then if you look at this matrix, you can have a 1 here and a minus 1 here and a plus 1 here. And
Because it is
can you just
it is
multiply?
a row of identity matrix, so only that is 1. So multiply this with that submatrix.
No, but it might have multiple rows. So my submatrix may have a +1, a -1, and a corresponding 1 from here. And maybe there is another +1, there is a -1, and there is a +1 here. Some such thing. And this may also have a +1. So if I multiply this by 2, like I said, it's possible that this gets multiplied by 2. Okay, I'll think about it. Really, you guys can also think about it. I mean, there are two things. One, maybe, it's also possible that this, if you include this, it's probably not unimodular, but probably doesn't matter. Okay, we should try some example and check it out whether it's actually really totally unimodular if you include this as well. Or the fact that this is an identity matrix may be useful. Did I pick a submatrix of identity matrix? Yeah, maybe. Some sort of an induction, maybe, that you pick some submatrix of an identity matrix, submatrix of a totally unimodular matrix, and put them together and find the determinant. It may be again plus or minus 1 or 0. Okay, check that out as an exercise. We'll look at it next time. So net, what we have is that using strong duality theorem and this totally unimodular implies you have these integral vertices. We have in a bipartite graph, maximum matching is equal to minimum vertex cover, and in a general directed graph, max flow equal to min cut. And these things have independent combinatorial proofs as well. We actually saw max flow equal to min cut theorem independently, but they are all sort of special cases of this LP duality.